Hi, welcome to our very first podcast ever, A Gal's Guide to the Ocean. You're here with your host,
Catherine.
and Jadee, and today we will be focusing on SLO 2, the topic being
Atmospheric circulation. So firstly, the atmosphere is made of gases such as nitrogen and oxygen, which are the main ones, and the others that aren't like as big are argon, helium, carbon dioxide, and others. So the atmosphere isn't actually just one part. It's made up of three regions, and those regions are the troposphere, stratosphere, and mesosphere. These regions all have their different placements, such as the troposphere being the lowest and extending up to 6 to 10 kilometers. And next is the stratosphere, which extends up to 50 kilometers. And lastly, the mesosphere, which is the farthest away from the Earth, is it extends 50 to 85 kilometers above the planet.
That was really interesting, Catherine. I really enjoyed your take on that. I'm gonna be discussing the Earth's heat budget, which is actually really interesting. For those of you who haven't maybe studied it or have a clue what it is. So it's basically like a balance of incoming and outgoing heat on Earth. So a while back, we had a group present the heat budget, and they drew on the board, they drew like a circle to represent the Earth, and then they drew an outer like line surrounding that Earth. And that was kind of like the representation of the atmosphere. And so what that is, or like displayed, was the energy that's absorbed by the Earth. It returns to our atmosphere through three specific processes. You may ask, what are the processes? Like, I haven't studied this. And so those processes are conduction, radiation, and latent heat, which is the phase change. Conduction is actually the transfer of heat through the direct contact between the surface and the atmosphere. So that's why I was talking about the diagram that they drew on the board earlier. It was like the little representing of the atmosphere, which is the heat through direct contact. So that's like the direct contact would be like the line on the displayed image. As for infrared radiation, that is basically heat that's radiated in the form of a long wave from all the bodies of temperature above absolute zero. So if it's above absolute zero, it's completely relevant. That is also the basic structure for the greenhouse effect. The greenhouse effect, a lot of us have studied it since we were in middle school, and it is basically when it's when the energy is coming through the
The particles in the atmosphere trap the sun.
yes,
The sun's heat.
the particles in the atmosphere trap the sun's heat, and so that's how we're impacted by it. That's why it's so important in all the studies throughout middle school and even high school and now, and it remains very relevant in the Earth's heat budget because it's one of the main ways that the energy is transferred through our atmosphere.
And how we keep the warmth.
Definitely, Catherine. I love that. And also, some of the radiation of that passes through the atmosphere, but a large amount of it is actually absorbed and then re-emitted throughout different directions by the greenhouse gas molecule. So it distributes everywhere. And of course, the heat exchange between the Earth, which would be like the land or the ocean. That's why it's so relevant to oceanography. And the atmosphere is latent heat transferred through phase changes, which would be the largest pathway for that heat exchange. So it's like the main one.
Okay, so next we'll be talking about the wind and Coriolis effect. So starting off with the equator, since it's so warm, the air is less dense, which is where it rises. Compared to the poles, there's obviously cold air, which is when it sinks. When the air is moving, it results in a large convection cell for each hemisphere. This then is responsible for the winds. The way the winds are changing direction is by the Coriolis effect.
What is the Coriolis effect, Catherine?
Good question, JD. It's a direct result of a different latitudes on our planet that rotate at different speeds. So it's also responsible for describing the pattern of deflection taken by objects not firmly connected to the ground as they travel long distances around the Earth. So in the northern hemisphere, the Coriolis deflection will be to the right side since it is going from high to low speeds. And in the southern hemisphere, the Coriolis deflection is to the left since it's from low to high speed.
Good input, Catherine. I did not know, I previously had known what the Coriolis effect was, but I think you described it in a way that's easier for me to remember, so I really appreciate that, as do our viewers, I think. So basically, continuing off of what you said, weather and temperature have a lot to do with it. So cold air will start in the poles, and then it gets pushed down by other air that warms up the equator. And that's basically how the Coriolis is occurring. And so that the warming up and the air pushing, it's again towards the poles. And I think you mentioned the equator earlier as well. Mm-hmm. That forms a convection cell. Yes. Now, you're probably like, what's a convection cell? And that's a great question because I previously had not known what a convection cell was. And it is basically just a system where the fluid is warmed, so basically the water. Therefore, it kind of just loses some density because of the temperature. Like I said before, temperature has a huge effect on the ocean system in general. Mm-hmm. So due to the rotation, basically going off, due to the rotation of the Earth and this Coriolis effect, there are three major cells per hemisphere known as the Hadley cells, Ferrel cells, and polar cells. Now you're probably like, this sounds familiar. It's not really familiar, but if you do recall, 3 is an important number because earlier on in the podcast, we talked about the 3 phase stages. And so 3 is just a really important number. So if you ever need help remembering how many phases there are or how many cells there are, remember that the magic number is 3. Yeah. So now you're probably like, what are Hadley cells? And they are the convection cells between 0 degrees and 30 degrees. And these are created by rising air at the equator and also the sinking air at 30 degrees. Going off again, the Ferrel cells are between 30 degrees and 60 degrees. They are created by the sinking air at 30 degrees and rising air at 60. Now, going off again, the polar cells are between about 60 degrees and 90 degrees, I believe. Yes. And those are created by the cold air from the poles that sink at 90 degrees and then rise at 60. Mm-hmm. So these numbers are very, what's the word? They
basically go off of each other. Like the Hadley cells are the lowest, then Ferrel cells are the middle, and then polar cells are the top.
Definitely. And they're all very constant. They all go off of 30-degree increments. Yes. So it's not really it's not too hard to get.
3 again.
Again. Yeah, so it's remember the magic number 3. And it's not too bad to where you can get lost. Just remember the number 3, and as well as it's going in increments and staying constant, which is easier for us to remember. And then how you're probably asking how does this affect the wind? I get Coriolis, the Coriolis effect, but how does it impact the wind? And that's also a really relevant question. So the winds are created by the convection cells. So that's why we were talking about convection cells, of course. And they're named after the direction from which they originate, not where they're going. So where they start, not where they're going to end up. So going off of this again, the Coriolis effect deflects the path of the winds to the right in the northern hemisphere and then to the left in the southern hemisphere. So it kind of it's kind of like if you get a foil paper and the sun is coming onto you, and instead of coming onto you, you're getting that foil and you're deflecting it onto somewhere else. So let's say that is let's say as an analogy, right? You're holding a foil paper. You're the northern hemisphere, and that's like that sun as an analogy, right? It's going onto you, the northern hemisphere, and you're deflecting it to the southern hemisphere, which would be like another person. You're deflecting it onto that other person.
Bouncing off, basically, like.
Yeah, so you're bouncing, exactly, Catherine. You're bouncing it off, just like the Coriolis effect deflects the path of the winds, which I know you talked about earlier, deflection.
Yes, yeah, I did.
And
And just more clarification.
Yeah, so it's basically just clearing up any maybe confusion or doubt that you may have. And so this deflection leads to the pattern of prevailing winds. Between the equator and the 30-degree latitude are the trade winds. And the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere, as well as the westerlies being the dominant winds between 30 degrees and 60 degrees in both the northern and the southern hemispheres. So that's pretty cool and definitely some food for thought.
Right.
So just as there's a westerlies, there's also the opposite, which would be the easterlies, the polar easterlies actually. And those are found between 60 degrees and the poles.
We have a picture for you guys to give a visual.
Yeah, so we're going to be adding visuals just to make it easier to follow along with us, so that way you can have
Good visual representation.
a good representation as well as being able to understand what we're talking about. It's definitely easier to correspond with. And in between these wind bands, there's regions of high and low pressures. So the high pressure zones is where the air is descending. So it's going down, it's pushing down, while the low pressure zones are rising up. So there's going to be arrows, and it's kind of like it's creating a conflict. Like one's pushing up on the other and the other's pushing down on the other. And it's very just conflicting. It's like the complete opposite, basically. Along the equator, however, the rising air, right, the bottom one that's going up, creates a low pressure region, and that's called the doldrums. Or other people can call it the ITZ, I believe, and that stands for Intertropical Convergence Zone. It's kind of a mouthful, that's why it's easier to call it the doldrums, I feel personally.
Yes, I agree.
And this is just a convergence zone that shows the trade winds converge. Excuse me. And so basically at 30 degrees, there are high pressure zones of descending air known as the horse latitudes or the subtropical highs. It's also a mouthful. And then going on at 60 degrees, remember the 30-degree increments, lies a low pressure region called the polar front. These high and low pressure zones, they're very correspondent depending on the type of season that we're in, because everything has to do with Earth's rotation, and so that's how we have seasons, right? It doesn't just magically happen. Everything's, of course, created by an outside force. So this causes important effects on our regional climates, and so that's why it's dependent and correspondent to the season.
Okay, so moving on to winds and climate. As I discussed warm air earlier, this air at the equator is full of water vapor, but when it continues to rise in the atmosphere, this will cool down due to being farther away from the equator. When it cools down, the water vapor cannot be held anymore, which results in condensation, then the formation of rain. The way the climate gets affected is the elevation of land, which creates rain shadow. What rain shadow is when the air passes over mountains to the leeward side, which turns into dry air. But when this sinks, the pressure increases, which will heat the air back up, and the moisture will evaporate. Dry desert regions are then created behind mountains, which is the rain shadow that I said earlier.
So basically, continuing off of what Catherine was talking about for the winds and climate, Another important factor, not only are the mountains important, but also like the ocean, because we are talking about oceanography after all.
Right. This all connects.
Yes, definitely. So the sea breeze is important, and that is actually created during the day when the winds are blowing from water towards land. So sea breeze is when the water is pushing wind or air out into the land. So kind of like when you're at the beach and you're sitting on the seashore and like a big breeze of wave, or like the waves are coming and you feel that breeze. That's what the sea breeze is. And so during the day, the land also heats up faster than the water because the cool winds descend into the water, then pushes towards the land, which then heats up and rises on the land. It's kind of confusing, but we're going to put some diagrams on here for you to understand kind of what we're saying. However, land breeze is a complete opposite. It occurs at night, not during the day, and the winds blow from the land towards the water. And at night too, the opposite happens, and the land becomes like cooler than the water. So the temperatures, like I said earlier, the temperatures have a lot of effect. The air descends on the land, then pushes towards the water, heats up, and rises near the water. There's a lot of arrow action going on here. Which also we talked about earlier was seasons. So seasonal winds have a lot of important play too. They follow a kind of same pattern. During the winter though, the low pressure is over the warmer ocean and high pressure is over the colder land. Kind of the opposite too. So winds blow from land to sea and the other ones are from sea to land. Now, during the summer, the land is warmer and than the ocean, of course, which a lot of us go to the ocean during the summer, which causes low pressure over the land and winds to blow from the ocean towards the land. This is also correspondent to like monsoons during the summer, and those are actually caused by winds blowing from the ocean containing a lot of water vapor, which is basically the system of like evaporation and all that. Like when the water is like, it becomes vapor because of the sun and the clouds, that basic gist. And as the moist air passes over the land and rises, it cools and condenses, causing seasonal rains. So that kind of just concludes our whole
First
spiel.
episode.
Yeah. So this is the pilot, and we really hope you enjoyed it and maybe learned a couple of things along with us, because this was definitely a learning process.
Okay. So
Goodbye. Bye.